going over re-expressing data practice problems now. So this is the last section of Unit 2, just going over some practice problems in this section. Again, if I'm moving too quick through these, remember to pause these so that you can copy them down, and then we can go through it. If I go any slower, these videos will be hours upon hours long, and they already are pretty long. But anyway, so let's take a look here at the first one. It says, suppose you have fit a linear model to some data, and now take a look at the residuals. For each of the following possible residual plots, tell whether you would try a re-expression, and if you would, why. So it says for each of the residual plots. So basically, here's how it works. If you think that you're going to do a line, right, and you think it's a straight line, if you don't see a pattern, more than likely I'm probably going to keep it and say the linear model is good. To me, this looks like a pattern, so it's probably not good. These are the ones where kids have a more difficult time deciding. It looks like there's no pattern, but then it looks like there is, kind of like a fanning out. Fanning out is still partially like a pattern. So it says, for part A, the residual plot shows no pattern, so no re-expression is needed, meaning you probably did a good job by saying let's do a linear regression with that. But take a look at B. This shows a curve, which is what it's saying. So it says you probably want to try to re-express to straighten it, meaning maybe we log the x's or log the y values to see if that helps, so that then we could use the line reg. And then this one, it's showing like a fan shape. So it says that we would also try to re-express this to equalize the spread. And think about it this way. There's no pattern. That's a pattern. This pattern looks like it's fanning out. It's still a pattern of fanning out, which is why if you want to view it like that, that's why you'd probably want to re-express it. So same types of problems. Now look at these. To me, this one, looking ahead, that looks more scattered, like there's no thing. This is fanned other way, so I would definitely try to maybe log the x or log the y. And this one even has a little slight bend to it, so maybe we'd want to do that. But it says that this residual shows a curve, so it says to re-express it as a straighten it out, maybe by doing the logs to it. This one, again, has a fan shape, but in reverse, it says re-express it to equalize the spread somehow as well. So you might want to see what you could do with that. Again, try the log technique, maybe a square root technique. You could try flipping it with the reciprocal. But again, this one, I'm not seeing a pattern, which means you're probably good with it being a linear regression. So in Chapter 9 and Exercise 9, we created linear models describing the trends in the number of passengers departing from Oakland. All right, and that from that airport each month since 1997. And here's the residual plot, but with lines added to show the order of the values in time. So basically, it's just trying to connect it to show you. But these are all the residuals. Here it would be 0, right? And basically, when you're looking at this, you're trying to see if there is a pattern at all. And it might be harder to see if there is or isn't. But the point is, can you account for the pattern shown here? All right, and then would a re-expression help us deal with this pattern? So basically, this is the other part of the problems. Notice the wording of the question, right? It looks like the residuals cycle up and down because there's an early pattern in the number of passengers departing, as in like it looks like they just kind of keep going like this back and forth, right? Looks kind of like they keep that type of pattern, and sometimes it's easier to see these patterns if you're looking at it and connect those lines. But because it sees because you can see a pattern, the point is a re-expression would be helpful. And because a cyclical pattern such as this one cannot be helped by re-expression, you would try to, all right? But it says a re-expression should not be tried, because what they're getting at is because it looks like it keeps going up and down from experience, they're saying that anything that does look like that, some kind of cyclical pattern, it can't help. There's nothing you can do to re-express it. I mean, you could try it if you didn't see the pattern, but it might not help it out very much. It says we examined the wind speeds in Hopkins Forest over the course of the years. Here's a scatter plot that we saw. And when I'm looking at the scatter plot, it does kind of look like the scatter plot itself kind of has a bend in it if you're looking at the data, right? This kind of looks like that. The point is describe the pattern that you see, all right? And then should we try re-expressing either variable to make this plot straighter, okay? Now, this is even average wind speed. Remember what we said in the last section about averaging things together. It makes the points more concise, closer together, right? Which is why they aren't as spread out. So the plot shows kind of like a wave pattern, indicating a pattern that continues year to year as part of an annual cycle, right? Kind of comes down a little bit as average wind speed, then it kind of takes off. And then it says, to re-expression should not be tried again because a cyclical pattern such as this one cannot be helped. So when you're seeing an up and a down, all right, what they're trying to get at is oftentimes there isn't anything that you can do to change that pattern if it's like a cycle, all right? Because what will probably happen is, even though we didn't see this, if we started over, it will probably go up and down again, and up and down again, because it's probably associated with the times of the year, that it looks like it dips down around this number of days, and 150 days in is like around the summer. The winds aren't as nasty as they are probably in the spring and in the fall as it keeps going. So for each of the models listed below, predict Y when X equals 2. So all they want you to do is, you know what, plug in 2. So I plugged in 2, and you can use a calculator to do it. And when people are looking at this, simple math, if you don't know how to solve it, to get rid of a natural log, you basically take each side to the E. And that's why it's e to the 0.28, which is 16.44. For this one, if I plug in 2, to get rid of that, you'd square both sides, which is why it's 7.84. Part C here, plug in 2, I get all this, but I could multiply by the y and then divide by 2.8, which is why it's 1 over 2.8, which is roughly 0.36. With this one, if I plug in 2, you can just straight up plug that in the calculator to get that answer. And then with this one, if I plug in 2, I end up getting this. But remember, when there's no 10, or when there's no number listed, that number is 10. So you take each to the 10 and then bump everything up as a power to get that answer. Taking a look at all of these, again, if I plug in a 2, that's just what you get. Again, I'm just plugging in a 2 so that you can see for B, hey, remember there's no 10, so I take it to the 10 to that power. Over here, if I plug in a 2 to get rid of natural log, it's like there's a little e there, so I take everything and bump it up, e to the whatever power. Over here, when you plug it in to get rid of a squared, because you decided to square both sides, I would square root it to get 1.67. And then e over here, when I plug in a 2, I would multiply by the root y, divide by that, and then square it. Technically, you need to square the top and the bottom, but squaring 1 is just going to give you 1 anyway to give you your answer. Just some simple substitution and then solving, as all those are, solving some equations. Taking a look at this one, it says, as the example in the chapter indicates, one of the important factors determining a car's fuel efficiency is its weight. So let's examine this relationship again for 11 cars. And it says, describe the association between these variables shown in the scatter plot. So as I look at this, it's looking like fuel efficiency in miles per gallon and their weight. It looks like it, for these 11 cars, it's going down, right? So that's what it's looking like. So it says, describe the association. So the association, and then it says part B, here's the regression analysis. What does the slope of the line say about it? So that's the slope of the line. Looks like it's negative and going down. And then that's the y-intercept, which is up there around 47. And that is the weight. So as the weight, it's looking like it's saying, as the weight goes up, roughly, and I guess this is in terms of thousands of pounds. So as it goes, for every pound, which I guess it's not a pound, it would be thousands of pounds. For every 1,000 pounds, it would go down about the fuel efficiency of down 7.65. But anyway, to describe it here, and then part C, do you think this linear model is appropriate, and use the residual plot to explain? Like, do you see a pattern? It's kind of looking like with the residuals, it's going down and then back up again. Is what it's looking like. So it kind of depends. It looks like it could be a pattern, so we'll take a look here and see. So the association between the weight and gas mileage of cars' efficiency, it's definitely looking like it's more linear, right? Because it's going down, it's looking pretty strong for the most part. Nothing's too far off, like no points all over the place, but it's definitely negative. So it's appearing right now that the heavier the car tends to have lower gas mileage. Heavier the car, the lower the gas mileage. That's the association that it looks like we are seeing. But looking at this, it says for each additional thousands of pounds, right, that we have, because that's the slope, for each additional thousands of pounds, it looks like we're predicting a decrease of 7.652 miles per gallon of the car, because it's decreasing that much. And then it says, do you think this linear model is appropriate? It says probably not, and it's like I said before, it looks like it's kind of curved, right, with a pattern with the residuals. The model tends to underestimate the gas mileage for cars with relatively low and high gas, right? So like here and here, it's underestimating. Like if you look at the residuals, these are good estimates, but everything else is kind of out there as well. So if you notice that, the lower and the higher the gas mileages are, it's not really doing a good job of predicting them. So an overestimate of the gas mileage of cars or underestimate. All right, I'll pause it there, and then when we come back here, we will start up revisiting, I guess, this problem with the fuel efficiency and the gas consumption.